So in this 30th lecture, I'll discuss the topic charge densities or charge density in semiconductors. Now, the aim of this topic is to understand that what are the charge densities means. Suppose you can have an intrinsic semiconductor or extrinsic semiconductor. If this is a semiconductor, suppose I say it is an n-type semiconductor, it will have majority of electrons for n-type. Suppose this is n-type. You will have large number of electrons and less number of holes as compared to electrons. These negative are representing electrons, these are holes. So in this topic, we are interested in these charge carriers, majority charge carriers as well as the minority charge carriers in a semiconductor. Now, suppose I say that this is an intrinsic semiconductor. Suppose this is a semiconductor here. I make this as a suppose this is a semiconductor here. And it is an intrinsic semiconductor here. This intrinsic semiconductor, of course, will have certain number of electrons and holes. It is made extrinsic either n-type or p-type by adding some donor impurity or by adding the acceptor impurity. And of course, by adding donor impurity, you will have excess of electrons, and by adding acceptor impurity, you will have excess of holes along with the intrinsic holes and electrons. Now suppose I assume that you have a semiconductor here, an intrinsic semiconductor is there initially, and suppose I say that the intrinsic concentration is Ni. Ni is the intrinsic concentration, N is the whole electron concentration, small n is the electron concentration. When I say electron concentration means number of electrons per unit volume. It is number of electrons on unit volume. Similarly, P is the whole concentration or the number of electrons per unit volume. N with suffix D is the donor concentration, means number of donor atoms per unit volume with which the intrinsic semiconductor is doped. Similarly, if Na is the acceptor concentration and Ni, I have already told you, it is the intrinsic concentration. Now just try to understand this. What do you mean by this? First of all, suppose I say that this is an intrinsic semiconductor here. It will have some electrons and holes, and equal number of electrons and holes, I can say. Initially, this is an intrinsic one. This is intrinsic, having equal number of electrons and equal number of holes. Let's say this is intrinsic, electrons and holes. Now what happens when I make a system n-type? What happens with n-type system? I told you that you have an intrinsic semiconductor. It is doped with donor impurity. Intrinsic semiconductor is doped with donor impurity. Now what will happen when it is doped with donor impurity? Means it is a pentavalent impurity with which the semiconductor is doped. That is, you have intrinsic semiconductor. This intrinsic semiconductor is doped with donor impurity. Every donor impurity releases its fifth electron. Every donor impurity will release its fifth electron and it will become a donor ion. So when it is doped with donor impurity, what will happen? That you will have, of course, intrinsic semiconductor. When it is doped with donor impurity, this donor impurity will become a donor ion, positive ion, because every donor impurity releases its fifth electron. It will have majority of protons, so it will be a ion, donor ion. So one electron will have one donor ion. If the concentration is Nd, you will have total Nd ions, and of course with the release of an electron, with the release of electrons is there. So it is very clear that when donor impurity is added, large number of electrons will be there and this donor atom will be there. So when it is doped with donor impurity, so let me write it. When intrinsic semiconductor is doped with donor impurity. That is, Nd is the donor concentration. So I can say that this intrinsic semiconductor plus donor impurity, suppose Nd, donor impurity is Nd, this will result in donor ions, Nd number of donor ions per unit volume plus electrons. Of course, Nd number of electrons will be there. So it is very clear that here you will have a large number of electrons. If you see, it will have large number of electrons here, along with the donor impurities, which is positive donor impurity. You'll have Nd positive, Nd positive, Nd positive, Nd positive, Nd positive. So this is what happens. Now suppose same semiconductor, I say when you have doped with Nd, this is the situation. Now if this semiconductor is doped with acceptor impurity, if this is made p-type, the same semiconductor, if this is made p-type, that is, if intrinsic semiconductor is doped with acceptor impurity. Now every acceptor impurity, it releases Na, it releases an electron, it accepts an electron, and when it accepts this atom will accept an electron from the system, it will become a negative ion, Na negative, and plus the release of holes. So every acceptor atom will become a negative acceptor ion by accepting electron, and of course it will release a hole, or from where the electron is accepted you will have a hole there. So Na number of acceptor impurities will have Na negative ions and Na number of holes. So here I can say when intrinsic semiconductor is doped with acceptor impurity, when it is doped with acceptor impurity, that is, I can say this intrinsic semiconductor plus acceptor impurity means this acceptor concentration, it is added with this much of acceptor impurity per unit volume. Of course it will release holes, positive holes, and this acceptor atom will become a negative acceptor ion. So now what will happen? This semiconductor, if you see this semiconductor, the same semiconductor, when it is doped with acceptor impurity, you will have negative acceptor ions here. You will have negative acceptor ions. I am showing this way. Negative acceptor ions. This is a negative acceptor ion. This is a negative acceptor ion. A negative acceptor ion. And with the release of holes, of course this will release hole also. It will release holes. Now if you see, the total positive charge is equal to total negative charges. Now since the semiconductor is electrically neutral, I can say since semiconductor is electrically neutral. Electrically neutral means this implies that total positive charge is equal to the total negative charge. And what is the total positive charge? Initially you had the intrinsic electrons and holes. Now this donor impurity has least electrons and has become positive donor ion. Acceptor impurity has accepted electrons, least holes, and has become negative ion. So if you see, these are the holes and electrons, positive charges. So total positive charges are Nd plus P. These are the holes, whether intrinsic or released by this acceptor impurity. Positive, and this positive charge here, Nd. So total positive charge is Nd plus P. So I can say that the total positive charge, I can write this as Nd, which is the positive charge. How many positive charges will be there? It is equal to the donor concentration. If there are 5 lakh donor concentration per unit volume, if there are 5 lakh donor atoms per unit volume, there will be 5 lakh positive ions here. So it is equal to the number of donor acceptation. Nd plus the number of holes per unit volume is equal to negative charge will be Na plus the number of electrons. Number of electrons per unit volume means initially there were some intrinsic electrons and some released by this donor one. So this is the general expression I can say till this is electrically neutral. So suppose I say this is expression number A. Let me rewrite this expression once again, that this Nd plus P is equal to Na plus N. I am rewriting this equation here. That is, you have Nd plus P is equal to Na plus N. Suppose I say that this is equation 1. Now let's take the different cases. I am interested in the charge densities. Now I'll say for N type semiconductor, I'll take another heading, that what will happen for N type semiconductor. For N type semiconductor. Now how N type semiconductor is formed, just try to understand this. For N type semiconductor, you have an intrinsic semiconductor. This is an intrinsic one. It is doped with donor impurity. So there is no concept of, there is no sense of acceptor impurity here. If I have to make it N type, this will be N type. This will be made N type now. This semiconductor will be made N type. For N type semiconductor, value of Na is equal to 0. Very first thing is that. So in this equation, I substitute this Na is equal to 0. Therefore, I can write this Nd plus P is equal to N. I hope this is clear to you. This Nd plus P is equal to Na plus N. Or I can say that this Nd is equal to N minus P from here. Nd is equal to N minus P. Now, when I made this N type, when this is made N type, it is very clear that the electrons are far greater in number. These electrons are far greater in number as compared to holes. Let me make a bigger figure. This is what it is. These electrons are in majority and the holes are in minor, are the minority charge carriers. These are the holes. And now since these number of electrons are far greater than or are majority charge carriers as compared to holes, therefore I can say that the number of electrons is approximately equal to, I equate this factor is equal to 0, although this is not 0. It is an approximation. N is approximately equal to Nd. Now I am using one more term here, N, and I am using here N with suffix N. Means the number of electrons in N type semiconductor. N is the number of electrons, and this N, which I have written with in suffix with red pen, this indicates which type of semiconductor it is. So the number of electrons in N type semiconductor is approximately equal to Nd. That is what I am interested in. I am interested in the number of electrons in N type semiconductor and number of holes in N type semiconductor. This is what I am interested in. Now, number of electrons is approximately equal to this much. Now, I know that by mass action law, I discussed in the last lecture, mass action law says that the product of N into P is equal to Ni square for any semiconductor, whether it is intrinsic, N type or P type semiconductor. Now, if it says that this is equal to this much, so it is applicable for N type semiconductor also. We are talking about N type semiconductor. So I can say that this N in N type semiconductor and holes in P type semiconductor, that is the product of electron concentration and hole concentration in N type semiconductor is equal to Ni square. So from here I can say that the number of holes, which is the minority charge carriers, is equal to Ni square upon number of electrons, or this indicates that the number of holes in n types, P is for holes and this suffix represents what type of semiconductor it is equal to Ni square upon number of electrons is approximately equal to Nd. So let's make an approximation only, Ni square upon Nd. So these are the charge densities in n-type semiconductor, that is the majority charge carriers is approximately equal to donor concentration and the minority charge carrier is equal to Ni square upon Nd. Let's take the second case for p-type semiconductor. For p-type semiconductor. Now what will happen in p-type semiconductor? Very first thing is that how p-type is made. Look at this, how p-type semiconductor is made. A p-type is made, you have an intrinsic semiconductor. This intrinsic semiconductor and it is doped with acceptor impurity. The resulting semiconductor is p-type. This semiconductor is p-type. So very first thing is that in this type of semiconductor Nd is equal to 0. It is made p-type by adding acceptor impurity. So Nd is equal to 0. So in equation A, I substitute this Nd is equal to 0. So I can say that this P is equal to Na plus N. Or I can say that this Na is equal to, I'll write this as Na is equal to P minus N from here. Now again I can say that since in p-type semiconductor, what will happen? Holes are the majority charge carriers. Holes are far greater than number of electrons. So I can say this implies that. I neglect this. I can say that this P is approximately equal to Na. Here this holes are majority charge carriers and electrons are far less in number as compared to this. So I can say that this number of holes are approximately equal to the acceptor concentration, and as I did in the previous case, I am talking about the holes and electrons of this p-type. So the holes in p-type semiconductor, P of P means the number of holes in a p-type semiconductor is approximately equal to the acceptor concentration. Let's find out the minority charge carriers. What will happen for the minority charge carriers? For minority charge carriers, I know again, since N into P is equal to Ni square, as per Mark's law action, N into P is equal to Ni square, and of course it is applicable to p-type also. So N P dot Pp means number of electrons in p-type semiconductor and number of holes in p-type semiconductor per unit volume is equal to Ni square, mass action law. This implies that from here I can find the value of number of electrons. Number of electrons in p-type semiconductor which are minority charge carriers, I can say it is equal to Ni square upon P of P. This upon this. And from here I can say that the number of electrons in p-type semiconductor is equal to Ni square. I write this as Ni square, and the holes in p-type semiconductor, I say it is equal to the acceptor concentration. Of course all are approximations. Approximately equal to Ni square upon Na. That is, I am neglecting the number of minority charges as compared to majority, although they exist. So I hope that this is clear to you, that the number of electrons or the number in n-type semiconductor approximately denote donor concentration, and the number of holes in n-type semiconductor is equal to Ni square upon Nd. The number of majority charge carriers for in p-type, that is the holes in p-type, is equal to Na, and the number of electrons in p-type semiconductor is equal to Ni square upon Na. I hope this is clear. The third case, if I take from here, that is if I take intrinsic semiconductor. Let's take, I'm explaining, I'm not writing it. Let's talk about intrinsic one. What will happen in intrinsic? Intrinsic means there is no doping. There is no doping means Na is equal to 0 as well as Nd is equal to 0 here. This factor is 0 and this factor is equal to 0. And of course, then you'll have the electron concentration is equal to the hole concentration that we already know, and it is equal to the intrinsic concentration. So I hope that this point is clear to you. The main point is that we apply the charge of the point of neutrality here. Total positive charge is equal to total negative charge, and the positive charge are nothing but the positive ions, donor ions and holes. Negative charges are the negative acceptor ions and the electrons. So total positive charge is equal to total negative charge. From here we have derived that what are the majority and minority charge carriers in case of semiconductors, whether intrinsic, N type or P type, which in general it is called the charge densities in semiconductor. So I'll stop it here. We'll do some numericals based on it in the next lecture. Thank you.